What's up, everybody? Hope you're all doing well today. We're going to be doing some circular motion review problems. I have 11 of these guys for you today. So I'd recommend taking a look at the link below and trying these out on your own. Or you could just kind of pause the video in advance of the solution. You'll get a lot more out of this if you try to solve these first. So without further ado, let's go ahead and get started. So in this first question, we have a restaurant atop the Space Needle, and it's slowly rotating so that folks can get a nice view of the city. So we're going to figure out how fast we're moving. So we're saying that the customer is 12.5 meters away, right? So just imagine, I'm sure the actual needle is much bigger than this, but let's just imagine they're on the edge right there, 12.5. We want to know how fast they're moving. So to find velocity, remember velocity is simply distance over time, right? But if you're on this circle here, so if our customer's right here, and they're going to be making a loop around, right? They're going to be traveling one full circumference. That's the distance they're going to make in one full revolution. And that's going to take 1 hour. So if we want to calculate that out, we'll go 2 pi, that's the circumference, right? And then the radius is 12.5 meters. And then that takes 1 hour. Now we do want to change this to seconds. So 1 hour is 60 minutes per hour, and that's 60 seconds per minute, which gets us 3,600 seconds. All right, so we'll just go ahead and multiply that out, and we get 0.0218 meters per second. So that's pretty slow. In fact, if you've ever done this either in Seattle, or they have many of these, I know in Los Angeles they have one as well, you don't even really notice that you're moving. You just slowly see the city rotate as you're eating your dinner. So anyways, the next part is let's find our centripetal acceleration. So remember, we're going in a circle here, and so there must be a centripetal acceleration changing our direction. So that's simply v squared over r. At this point, the problem is pretty trivial, right? 0.0218 divided by the radius, which is 12.5 meters. Oops, I almost forgot. Super common mistake. Forgetting to square. So go ahead and square that guy out, and you get, well, a very small number, 3.81 times 10 to the negative fifth. Again, super small number. If you've ever ridden on one of these, you don't even notice that you're moving, that you're accelerating. I'm going to add a bonus question here. What about the angular velocity? So angular velocity, remember, that's basically telling you how many radians you're traveling per second. Okay? Well, we're going 1 revolution per hour, or 1 revolution every 3,600 seconds. So that means in 1 revolution, we're going to be going 2 pi radians per revolution, right? Every revolution, we're going to be going 2 pi radians around. So therefore, our angular velocity, which we use the symbol omega for, is going to be 2 pi divided by 3,600, and I get 0.00175 radians per second. All right, let's move on to the next one. So in this question, we have our car, and we're going to round a curve here. And this curve has a radius of curvature of 65 meters. Okay? Now, in order for us to turn, there needs to be friction, right? There needs to be some friction. That's actually what provides the centripetal force that keeps us in a circle. All right, so to set this up, so again, we need this force towards the middle, or force of friction. Let's kind of do a free body on this. So if we sum up our forces, our horizontal force here, which is, I just want you to notice, I'm going to call it horizontal because I'm looking at it at like this position right here. But the force is actually changing continually. So just from this starting perspective, let's call this point A, our friction's horizontal, right? So anyways, that force is going to be just simply friction. And this is what keeps us in the circle. So this is going to be our centripetal force. Now the rest of this, let's draw maybe a rear view. If you imagine looking at it from the back, we also have good old FG and good old normal, right? And visually this would be the friction coming this way. So, in the y direction, you all know this by now, it's just this simple F normal minus gravity equals ma equals 0. So the normal force is just going to be mg here. So I forgot what we're looking for. What are we looking for? We are looking for the speed. So how fast can we go? So if we go too fast, there's not going to be enough friction. We're going to fly off the road. So we're looking for that max speed. So friction is mu times normal, and AC is v squared over r. Now again, on this flat surface, Fn is going to simply be mg. That equals mv squared over r. Notice what happens, our masses cancel. So in fact, mass is irrelevant here. It's not irrelevant. Conceptually, let me explain conceptually. If you look at this here, the bigger mass, if we have a bigger mass car, it means that we need more friction to go around the turn, right? The bigger the car, the more force it needs to move it. However, if we have a bigger car, that means the normal force is greater. And if the normal force is greater, then the friction is greater, right? And so those two terms cancel out. We need more force, but we have more force. And therefore, they just cancel each other out. So let's continue the problem. We're solving for v, right? So this would be r times mu times g equals v squared, or v equals the square root of r mu g. Let's plug in the numbers for this. So the radius was given as 65, mu was given as 0.54, and little g is little g. Okay, solve that, and you should get 18.5 meters per second. So again, that's the minimum speed. If we go faster, we're going to start skidding out. If we go slower, we're good to go. All right, let's move on to the next one. All right, in this problem, we have a stopper. This is basically the lab that we did in class. We have a stopper here that's going to be spinning in a horizontal circle, but it's going to be at an angle here. So it says it's at an angle of 18 degrees with the horizontal. So that's 18 degrees this way. The string length is 28 centimeters. And we're just going to solve a bunch of things. So as usual, one of the first steps we should always be doing is making our free body. So here we have Fg coming down, and then we have a tension going this way. So let me do this just kind of off to the side. So here's our mg, and here's our tension. All right, and as usual, when we have things at angles, we want to change it into just x's and just y's. So we have gravity going down, and let's call this component vertical, our tension in the y direction. Let's call this tension this way, tension in the x direction. So that when we do our summation, in the x direction, we have simply tension, right? Tension in the x direction. And in fact, that's what's keeping us in the circle, right? This tension here, the component of tension here is keeping us moving in the circle, keeping the stopper moving in the circle, not us. So anyway, that's going to be equal to MAC. And in the y direction, I mean, visually, hopefully you can see what's going on in the y direction, right? We have the tension vertical minus gravity equals ma equals 0. So basically the vertical tension is holding up the weight. All right, so the next thing we really should do is kind of fix our tensions, find our tx and ty. So for example, this is t. Let's draw a triangle here. This is our angle theta. This would be the cosine, t cosine theta, that's the adjacent side. Over here would be t sine theta, that's the opposite side. So this was our ty, this is our tx. So if we kind of break these equations down a little bit further, we got t cosine theta equals m, and then we'll go ahead and do v squared over r again. Down here on the y side, we're going to have t sine theta equals mg. So this is really the setup for these types of problems. At this point, we're just going to start solving for things. All right, so the first thing is to find the tension. So you just got to look at what you've been given and figure out, okay, which of these equations is going to help me out. And in this case, hopefully you notice, since we're given the mass, this equation and the angle, we'll use this y equation to solve for the tension. So this is going to be t, what was our angle? 18, sine of 18 equals the mass, 0.02 kilograms, don't forget to convert, times little g. Solve for the tension. Tension is going to be small, okay, as expected, because our mass is really small. So we're not going to need too much tension here. Next, we're going to solve for the velocity. So once you know this tension, we can just throw that in there to solve for our velocity. So we're going to go 0.634 times cosine of 18 degrees equals the mass again, 0.02, times our velocity, and then we'll divide by the radius. So this part's a little bit tricky. I just want you to notice the radius is not the length of the string. So let me draw this again for you. So this is the length of the string, but the actual circle that this is going in is going to be smaller than the length of the string. This would be the actual radius of our circle. So based on the angle that we were given this angle right here, right? 20. So if that's 20, that means this must be 70. So then the actual radius we want, let's call that r true. That actual radius is going to be the length of the string. And then we're on the opposite side here, length of the string times the sine of 70 degrees. Oops, did I just say 70? I just noticed it's actually 18 degrees. So let's just make that correction. This should be 72. 72, there you go. So our length of string was 28 centimeters or 0.28 meters, sine of 72. That gets me a true radius of 0.266. So it's not that different. I mean, the angle is really small, right? So it's not that different, but it is. So we'll plug that into this true radius way up here, 0.266 meters. All right, go ahead and do the algebra. At this point, I feel like we can all do algebra, right? Don't forget to square root though, and you should get a velocity of about 2.83 meters per second. If you need me to do the algebra in these videos, just write me a comment and maybe I'll start doing that for future ones. All right, how long does it take for 20 revolutions? So whenever you see this type of problem, like really you want to go down to our base like definition of velocity. So in other words, remember velocity equals distance over time. And in this case, it's 2 pi r over t. Because the distance for one revolution is going to be one circumference, right? So in this case, they're asking how long does it take for 20 times? So that means we're going 20 revolutions times 2 pi. Now again, we're going to use the true radius here because that's the actual circle that it's traveling in. And then we'll divide by t. And oh yeah, that we got to sub in that velocity, right? 2.83. All right, do some math. Okay, t equals that big mess. All right, maybe I'll do the algebra this time. 2 pi times 0.266 divided by 2.83. Solve for time, and we get about 11.8 seconds. Okay, all right, let's move on to the next one. All right, in this question, we have our roller coaster, loop-de-loop. We have a 5,000 kg coaster. The radius of the loop is going to be 10 meters. And we're just going to solve for things. So the first thing we're looking for is the minimum velocity. So notice there's a minimum speed we need in order to make it around the loop. So to figure that out, the first thing really we should do is our free body, as usual. So we're going to have a force of gravity coming down. And then notice the force, the tracks are pushing on the wheels as well. Now at the top of the loop, the track is also going to be pushing down. It's a little counterintuitive, but you know, the track can't be pulling it up. It's going to pull it down, just like an upside down road, right? Is basically what it is. So when we do our summation, we are going to have the force of gravity, and I'm going to make it negative because it's down. I'm going to also make the normal force negative because it's down. And then we set that equal to ma. And this is a circular A, centripetal A, because, well, we're going in a circle. Now the direction of the A is important because at the top of the loop, remember acceleration is always towards the center. So that means on the left it's going to, on the right it's going to the left, on the left it's going to the right, and on the top it's going down. So our AC is down. So how I'm going to do that is in my equation, I'm just going to make sure that's negative. Now some people will just make them all positive. The key idea is that they're all in the same direction. The gravity, the normal, and AC are in the same direction. Now the other key thing is what's happening at the minimum speed. So if we're going really, really fast, no problem, we're going to make it, right? And in fact, the faster we go, the harder the track's going to push back. But if we're going barely, when we barely make it, that means we're barely touching the track. So we're going to say the normal force is 0. We're approaching that limit. The normal force is going to essentially be 0. And it's only gravity that keeps us in the loop. So notice our summation turns into this. Fg equals mac. So the force of gravity is the weight. And then this is equal to mv squared over r. Masses cancel. And we're just going to go ahead and solve for, what are we solving for? The min velocity? Yep. So 9.8 equals v squared divided by 10. So we got 10 times 9.8 equals v squared. Square root both sides. And we get 9.9. So that's the minimum. If we go 9.8, we fall. If we go 10, we're good to go. All right, so we're actually going to be going, now we're looking actually at the bottom of the loop. So let's look at the bottom of the loop. At the bottom of the loop, our free body is going to change a little bit. Why don't I do this? Why don't I zoom in on the free body and then we'll zoom out later. So at the bottom, of course, we still have gravity coming down, Fg. But this time, the track is pushing up on us. In fact, the track's force has got to be greater than gravity. So I'm going to draw it really long here Because notice at the bottom, it's kind of heading down, right? And then it's going to change direction coming back up. Actually, we're not coming back up, but imagine in that circle here, we would be coming back up. So there has to be, to change our direction, there has to be more normal force up compared to gravity down. So when we do our summation, we will look very similar, right? Except for now we have our normal force going up. We have gravity coming down. That equals MAC. Now remember, we have to look at the direction of A. We have to consider that. Well, at the bottom, A is going to be towards the center, which is also going to be pointing up. So we'll just leave it as positive there. So this time we're looking for the actual normal force at the bottom. So we're going to go normal, we don't know. Gravity is good old mg. mg equals mv squared over r. So notice the normal force, again, I just want you to notice, this is going to be mv squared over r plus mg. So, you know, if we were just on a flat surface, our normal force would simply equal mg, right? Fn mg. We did that in the previous problem. But here, we have to consider that centripetal motion. So it's actually going to be greater. The normal force is going to be greater. All right, let's go ahead and solve it. So this is 5,000 times the v at the bottom was 20 divided by the radius of 10 plus 5,000 times good old low g. All right, go ahead and plug that in. And oops, I don't got the answer on the key, so I'm going to actually have to do it. So we're going to go 5,000 times 20 squared divided by 10 plus 5,000 times 9.8. And I'm getting about 250,000 newtons. All right, let's go ahead and move on to the next one. All right, so this question we're looking for, well, we got Jupiter and we got the sun. So here's the sun, here's Jupiter. And actually, I just realized we need to know the mass of the sun. I know in my class we derived this, so all my students should have it. But if you're not in my class, you should know that the mass of the sun, it's about 2. It's a little bit less. I think it's like 1.9, but let's go ahead and just use 2 times 10 to the 30th. So if you're trying to solve this on your own first, go ahead and use that as the value. So anyways, we are looking for the force. So there's going to be force of the sun pulling on Jupiter, the force of Jupiter pulling on the sun. By the way, a common question I'm going to ask is, which one's greater? Is the force on the sun greater or the force on Jupiter greater? And the answer is they're the same, right? These forces are equal and opposite. And in fact, you can see that from the equation, right? We're going to do the force of gravity. That's big G times the mass of the sun times the mass of Jupiter divided by the distance between them squared. And so you can see it doesn't matter if you flip these two, right? The number is going to be the same. But of course, Newton's third law is also true. And the forces are equal and opposite, right? Probably one of the biggest reasons why people get confused with that is they think about, oh, you know, Jupiter is moving really fast and the sun's not moving hardly at all. So they think the mass from the sun's greater. But remember, F equals ma. So the force is actually the same. The mass is greater. The acceleration is less. So that's the part that changes. All right, so moving on. At this point, we're just going to plug in all our numbers here, right? So I did the mass of the sun. Big G, that's just a constant, right? You should know that by now. And then we need the mass of Jupiter. So 1.9 times 10 to the 27th. And then we'll divide by the distance between them. So it's going to be 7.78 times 10 to the 11th. and we're going to square that distance. So don't forget to square it out. So I get a force of, it's a big force, obviously. These are huge planets and suns. Large masses have large forces. All right, let's find the velocity of Jupiter around the sun. So Jupiter's cruising around the sun, right? We want to find out how fast it's going. Okay, well, the centripetal force, again, we're doing our free body, the centripetal force is coming from this force of gravity. So Fg is the centripetal force. So the force of gravity we just found, this would be equal to mv squared over r, and we're solving for the velocity here. The radius, that's just the radius of the circle. Notice that that's the same as the distance between them, right? So the radius is the same as the distance between them. All right, so Fg then, we know that's 4.17, 10 to the 23rd. Okay, the mass, so what mass is this? Well, remember, whatever mass is attached to the AC, that's the object that's going in the circle. So in this case, that would be the mass of Jupiter. So 1.9 times 10 to the 27th, v squared, and then again, the distance between them is 7.78 times 10 to the 11th meters. All right, so go ahead and solve that out. Here, I'll do a little bit of algebra. I know I said I wasn't earlier, but that's all right. Let's go ahead and do it. So 7.78 times 10 to the 11th, 4.17 times 10 to the 23rd. So we're multiplying both sides by this, the denominator here. Then we're going to divide by the numerator, 10 to the 27th equals v squared. And then finally, once you get that number, I am actually not going to do that, but once you get that number, square root it, right? That's going to give you your v. So v is about 13,000. My key says 13,062. You can double check that for me. Write me a comment if it's wrong. All right, what's the period of Jupiter? So period would simply mean how long it takes for one full loop, right? So for that, we'll be using our 2 pi r over time. So that's going to be 2 pi. Again, the radius is the radius of that circle. That's the distance between them, 7.78 times 10 to the 11th. And we'll use this velocity up here. So about 13,000 divided by the t. So I get a t of approximately 3.74 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 seconds. So that's in seconds there. If we want to convert that to Earth years, we'll just do a little dimensional analysis here. So let's convert that to Earth years. So let's do it down here. 3.74 10 to the 8 seconds. So remember, we have 60 seconds in 1 minute. We have 60 minutes in 1 hour. We have 24 hours in 1 day. And in 1 year, we have 365. It's about a quarter. It's a little bit less, to be honest. I'll put the actual, it's 0.24, but basically a quarter. That's why every 4 years we have a leap year. So let's go ahead and plug this in. We got 3.74 times 10 to the 8th. Then we're just going to divide by 60 again, divide by 24, divide by 365.24. Let's verify that I get what the key says. 11 point, I'm getting 11.85. or about 11.9 Earth years. All right, let's move on. So for this problem, we're finding little g on Mars. So let's imagine we have Mars here. We want to find little g. Okay, so the concept for this, Fg, remember, is mg. Or is it? It's not actually mg. It's only mg when we're close to the surface. So in this case, we are finding, it's saying acceleration of gravity on Mars. We're going to assume that they're asking about close to the surface here. So when we're close to the surface, we can use mg. But if we're far away, or if we're close, we can use the actual equation for gravity, which is big G m1 m2 over r squared. Where in this case, r would be the distance from the center of Mars to the center of like whatever it is I'm dropping, right? I'm going to calculate little g based on, say, something I'm dropping. So in this case, these two m's, let's just write it. So this would be the m of Mars, and this would be the m of whatever it is I'm dropping. And this m right here would be the m of whatever it is I'm dropping. So those two cancel. That's nice. And you're just left with little g equals big G times the mass of Mars in this case, times the radius, and this would be the distance between Mars, the center of Mars, and the thing I'm dropping. Well, notice that the thing I'm dropping is basically at the surface. In fact, if the distance, the Mars radius is about 3.4 million meters, if I'm like a few meters above, it's going to be negligible, right? Even if I'm like several hundred above or even 1,000 above, it's going to be negligible. It doesn't really become big until you're way up there, maybe several kilometers. So anyways, at this point, we'll just plug this in and solve it. 6.67, 10 to the negative 11th. Mass of Mars was given to be 642 times 10 to the 23rd. And then we'll divide by the radius, 3.4 times 10 to the 6th. Don't forget to square that out. And when you do, you get a little g of about 3.7. Okay. If we want to compare that to Earth, we'd say, 3.7 divided by 9.8? It's about half, right? 3.7 divided by 9.8 is 0.378 times. Okay, maybe it's more like a third, a little bit more than a third. All right, that was pretty easy. Let's move on to the next one. All right, so this question, an orbit question. And you do need to know the mass of the Earth, the radius of the Earth. My students should have that number written down, but if you're not one of my students, you'll definitely need to know that number. So I wrote those down for you. So the concept of the satellite, basically, the satellite goes in a circle because force of gravity creates the centripetal force that keeps us moving in a circle. Right? So the force of gravity here is going to be basically the two masses, the mass of the satellite, the mass of the Earth, times big G, divided by the distance between them. So this is going to be our Earth to satellite. Now it's not the surface of Earth. It's essentially, I mean, you can see the circle here, right? It's the distance between the center of Earth to the center of the satellite. Now, unlike some previous problems, we're not close to the surface, so we can't just simply use like mg for fg. So that's why we're using the full big G equation here. And then we're going to square this out. So that should equal m. Now this m, mv squared over r, this m is the thing going in the circle. So this mass is the mass of the satellite moving in the circle. So notice what happens. The mass of the satellite cancels. And again, we've talked about this many times. The reason it can't, I mean, mathematically you can obviously see it, but conceptually the reason is, like if it's a bigger satellite, let's say the satellite was huge, if it was a bigger satellite, it would take more force to turn it, right? The bigger the object, the more inertia it has, the harder it is to turn it. So it needs more force to turn it. But if it's a bigger mass, there is more force. The gravity would increase on a bigger mass. And so those two factors cancel each other out. All right, so anyways, we're going to go ahead and solve this. So this radius is also the radius between the Earth and the satellite. So notice one of these terms will cancel as well. So this cancels and then this cancels, well, partially cancels, right? All right, so there we go. So v squared equals big G, let's just clean this up, big G mass of Earth divided by the radius or the distance between Earth and the satellite. So you do have to figure that out. So you could do it all in one big equation. I usually just kind of like to do it out on the side, so I'm going to do that here for you. So for example, what we care about, those two distances, let me draw these out for you. There is one distance, which is the radius of the Earth. Let's do it this way, radius of the Earth. And then there's another distance, that's the radius above the Earth, right? So here's the radius of the Earth. This is the radius above the Earth. So let's call this the true radius, is the radius of the Earth plus the radius above the Earth. So the radius of the Earth is 638 times 10 to the 6th. The radius above the Earth, in this problem, is 500 kilometers. So again, that's 500 kilometers is 1,000, right? So 500,000. So the actual true radius is 6.88 times 10 to the 6 meters. So just make sure you're using the true radius here when you solve for this problem. So v squared equals big G, which is 6.67 times 10 to the negative 11 times the mass of the Earth, 597 times 10 to the 24th, divided by, again, we're going to use this true radius here, 688 times 10 to the 6 meters. Okay, and then square root that. Once you solve for that number, go ahead and square root it, and I get about 76, I'm just going to go to 3 digits, so 7610 meters per second. So that's the speed that that the satellite needs to go to maintain that orbit. If we go too fast, by the way, we're going to go out of orbit. If we go too slow, we're going to essentially crash back down to Earth. All right, so the next thing then is, what's the period? How long does this take? So we'll use v equals distance over time, 2 pi r over t. We'll just use that velocity we got, 7610. We'll use the true radius that we also got, which is 688, 10 to the 6, and we'll divide that by t. So I get 5,680, if we go to 3 digits, seconds. All right, let's move on. So this is a common question you'll see on the AP test. It's just really, like, I refer to them as conceptual math questions. So we're just going to use our big G equation to solve this. And basically what you do is you just say, how are things proportional? So for example, F is proportional to the mass, right? So if the mass were doubled, then the force, if this was like 2m, then the force would basically be 2 times. Okay, easy enough. That's kind of all you do, honestly, on these. The distance one's a little bit tricky. So we say, F is proportional to 1 over the distance squared. So when you plug this one in, we're going to go 1 over 1/2, right? So 1/2, but then we're going to square that out. So that's 1 over 1/4, or 4 times. Now sometimes you just want to think about it conceptually. I mean, you definitely kind of have to do the math, but you think about it conceptually. Like if they're closer, so here's like part A, they're far away. If they're closer, you know it's going to be stronger, right? And since the radius is squared, If you cut it in half, it's going to essentially be 2 squared times larger, or 4 times. All right, what about if we do 2 things? So if the mass was tripled, so 3m means the force should be 3f, right? 3 times as big. And if the distance were doubled, so if the distance were doubled, remember force is proportional to 1 over the distance squared. So that would be 1 over 2 squared, or 1/4. So due to the mass, that would triple the force. Due to the distance, that would quarter the force. And due to both, that would be 3/4 the force. So honestly, that's really all you do on these type of problems. Let's do the last one just to finish things up. Let's do red here. So mass is tripled. If we have 3m, that means it's going to be 3f. If the other mass is cut in half, so 1/2 m, that's going to be 1/2. Right? And then the last thing is the distance is quadrupled. So if the distance is quadrupled, that's going to be 1 over 4 squared, or 1/16. So we got 3 times 1/2 times 1/16 equals 3/32. All right, that's all you do on those. Not too bad. You definitely should expect something like that on the actual AP test. They love that question. All right, the infamous Gravitron problem. So in this one, we have our Gravitron amusement park ride. We're going to get in it, and we're going to go against the walls. It's going to start to rotate, and we're going to stick against the walls. So if we do a free body here, let's say this is the wall, and then this is me. And I'm going to go upside down just for fun. So I'm upside down. Now the thing keeping me in the circle here is going to be the wall, right? That's what keeps me from flying out of the circle. So the wall is providing a normal force going this way. Gravity, of course, is trying to pull us down. And the thing that keeps us up is friction. So there's going to be friction between the walls and us that keep us up. So if we do our summation, we're going to have in the x direction just the normal force. That equals MAC. That's what keeps us in the circle, right? And in the y direction, we have friction that's keeping us from falling. Minus mg equals ma equals 0. So basically friction has to balance out with gravity, right? The force of gravity to keep us from falling. So how much speed do we need? Well, we'll go here. We know if we're finding speed, we're going to go mv squared over r. Okay. Now the normal force, we don't know the normal force. Or do we? Well, remember, friction is equal to mu times normal force. Equals mg. So we know, therefore, the normal force should be equal to mg over mu. There we go. There's our normal force. So if we now throw this over into our normal force, right there, so we're going to have mg over mu equals mv squared over r. Look at that. Masses cancel once again. Mass, mass. All right, and so now we'll just solve for r. Sorry, not r. We're solving for b, right? This thing's kind of messy. Let's shrink this over. Just kind of rewrite this in the corner, okay? So this is going to be g over mu equals v squared over r. This is mu. All right, now we can just solve for b, right? So v equals rg over mu. V squared equals that, and then square root of rg over mu equals v. Okay, so let's just plug stuff in. So the radius here was 10. Low g is low g. And the mu, this is the amount of static friction. It must be on there somewhere. There we go, 0.8. 0.8. Okay, plug that in. We got 10, we got 9.8. We're going to divide by 0.8 and then square root it. So I get 122.5. Square root of 122.5 gives me about 11.06 meters per second. So that's what speed we need in order to stick. Okay, if we go faster, we're good. If we go too slow, we will not stick to the wall. All right, let's find the period of revolution. Okay, at this point, I feel like we've done this so many times. You better not miss these when we take our test on this. So v equals 2 pi r over t. We'll throw in that speed, 11.06. 2 pi, the radius here was 10. And then we'll just solve for t. Okay, so I'm just going to assume my key's right, 5.68. If it's not, let me know in the comments below. What's the frequency? Well, remember, frequency is simply 1 over the period. So if we know the period, we know the frequency, right? So frequency is essentially how many revolutions per second. You can think of the period as the seconds per revolution. You can think of the frequency as revolutions per second. All right, and we get 0.176 revs per second, or the units we'll often use are hertz. All right, let's move on to the next one. So in this question, we have our circular space station. We're trying to simulate gravity in the space station. So what we really want to do, so if we look at our free body here, basically this is moving in a circle, and the floor is going to push back on our feet. So I do a more detailed analysis of this. I'm just going to assume you've watched that or you've done this problem before. But the key idea here is that the normal force provides the centripetal force that keeps us in the circle. And if we want this to be just like Earth, right? So if we're on Earth, here's me on Earth, right? On Earth, gravity and the normal force, like in a normal situation, gravity is equal to the normal force, right? So if we want this to be just like Earth, then our mg should equal our mac. Or essentially, g should be ac. So in that case, we're going to just simply solve for, we're going for the period, right? So let's keep going. So you could solve for velocity here. And probably I've had you do this in the past, where you find velocity, and then you could find the period. You know what, just for fun, let's just derive a massive equation for period. Yeah, I don't think we've ever done that. Let's go ahead and try that. So if the simple way to do this is to just find the velocity, right, and then use v equals 2 pi r over t. But what we're going to do is we're just going to solve for t. So let's do that. That would be a fun activity. So we'll go g equals, and then we'll throw that bad boy in there. So it's going to be 2 pi r, the whole thing squared, divided by t. Oop, t is also squared, isn't it? Divided by r. There you go. That's going to be 4 pi squared r squared over t squared r. One of those r's cancels. Remember, this is equal to g. Now we're going to solve for t, right? So t squared, let's multiply both sides by t squared. Let's divide by g. T squared should be 4 pi squared r divided by g. Or let's just do the whole thing just in variables. What if I gave you this question, I said, derive this with just variables. So this would be 4 pi squared r. My pen's dying. Sorry about that. 4 pi squared times r divided by g. There you go. That's with just variables. And now we can just go ahead and plug in numbers, right? So we have 4 pi squared times the radius. Now be careful. This says the diameter is 600. So that means the radius is actually only 300. And then we'll divide it by little g. All right, so if you did it like this, you should get, I'm getting 34.76. If I go to 4 digits, that's the time, right? 34.76 seconds. All right. If you did it in the two-step process I talked about before, you should still be able to get the same answer, okay? It'll just, it's probably easier to be honest, but you should know how to derive it if you need to. All right, the next one. What if you're on the outside of the space station, now you're moving to within 50 meters, okay? So conceptually, what's going on here is we're moving closer. So initially, this was like the diameter is 600, so we were 300 way out here. Now we're moving closer, so now we're going to stand at this 50 meter mark. All right, this one's, you got to be careful when you solve this one. So basically, the key idea here is no matter if you're here or here, wherever you are, the time is the same. So the time for one revolution, the period to go around, is the same no matter where you are. Okay, imagine if you're on Earth, for example, it takes 24 hours for us to rotate once, no matter if you live in Canada, if you live in America, if you live in India, if you live in Ecuador, it all takes 24 hours, right? So what we're going to do is we're going to find our new velocity. So we'll use velocity equals 2 pi r over t, and we're going to go and find our new velocity when we're closer. All right, so we'll use 2 pi, the radius is 50 now, right? And then we'll go ahead and divide by that new, or the time we got before, which was what, 34 point, I'm just going to round it up 30.8 seconds. So I get a new velocity of 2 pi times 50 divided by 34.8, about 9 meters per second, 9.03. All right, so those of you that found the velocity before, I didn't happen to do it, but if you did, you should notice that it's actually going slower. Okay, the closer you are, this is a key concept, the closer you are, the slower you go, and that's because you're traveling the shorter distance in the same time, right? So shorter distance in the same time means you must be going slower. All right, to actually find what little g is going to be, we'll use this derivation that we had earlier, where g is going to be equal to the v squared over the r. And that's the new r here, so 9.03, the new v, and the new r of 50. All right, so I get 9.03 squared divided by 50 gives me about 1.63 for little g. So notice the acceleration of gravity, or this apparent acceleration of gravity. Remember, this is not actually little g, just kind of our apparent acceleration is much less. The closer you get to the center, the smaller it's going to be. All right, let's move on to, is this our last one? Yeah, let's move on to the last one. So in this question, we have a car, it's traveling along, it's going to go over a little hill. So here's our car. We're going to go up a hill, we're going over, kind of on a little bump here on a hill. So we're looking for the normal force at the top. Okay, so we're going to do our free body. So free body, of course we have gravity pulling us down. And now you have a normal force that's going up, right? Normal force is going up. So one of the things to think about is the normal force greater than, let's put this as a concept question, is normal force greater than, less than, or the same as the force of gravity? So why don't you think about that before we answer it. So hopefully you didn't say the same, because that would only be true if we're on a flat, like a flat surface, right? So the normal force, remember the net centripetal force has to be to the center of our circle. So if this is our circle here, imagine our circle here, there has to be a net centripetal force towards the center here. So that means gravity is going to the center. The normal force we know is going up. So the normal force has to be less than gravity. Has to be less than, so that the net force is going towards the center. So when we do our summation here, we'll prove this mathematically right now, right? So we have normal force up, we have gravity down, that equals MAC. Now remember, we have to consider the direction of the AC. So in this case, AC is towards the center, so AC will also be negative. So when we solve for the normal force, what you're going to see is the normal force equals the force of gravity minus this MAC here. So yeah, so the normal force must be less than gravity. So let's prove it. Well, I guess we just did prove it. But let's go ahead and plug in the numbers here. So this would be mg, so 1200 times 9.8 minus our m, which is also 1200. And then we're going to go v squared what was our velocity here? 15 divided by the radius of the curve, which is 24. All right, so we're getting, I'm going to assume this is right, 510 newtons. If not, write me a comment and we'll fix it. So 510 newtons is what the normal force is. Again, compared to gravity, gravity would be 1200 times 9.8, the force of gravity, which I'm just going to round it, all right? So that's about 12,000 newtons. Wow, it's much less. All right, the next and final question is, what's the minimum speed so that it just starts to leave the ground? So this hopefully you can see, we're going to use this same derived equation here. So Fn minus Fg equals negative MAC. Hopefully you can see, like when we barely start to leave the surface, like the faster we go, so we go faster and faster, let's say we leave the surface, well, once we leave the surface, that means the normal force is 0, right? So when we leave the surface, the normal force is 0. So when we barely leave the surface, we're going to say it's kind of approaching 0 here. So therefore, negative Fg should equal negative MAC, okay, or positive if we want. So mg should equal MAC, masses cancel, g is essentially equal to AC. And again, conceptually, think about it. If there's no normal force, the only thing keeping you in the circle is mg. And in fact, g is the acceleration, right? That's the centripetal acceleration that's keeping you in the circle. All right, so let's just go ahead and solve it. So 9.8 equals v squared divided by 24. So v equals the square root of 9.8 times 24, which equals 15.3. I guess that's why the normal force was so small, huh? 15.3, you leave the surface, and we were traveling 15. So we were just right on the edge of jumping that track. All right, I hope this was helpful. Let me know, and I will see you in the next one. Have a great day.